Hello friends. So all this while, ever since we started this topic of complex numbers, we have learned various forms to represent complex numbers. And when we were talking about Argan plane and modulus, we said something about complex number vectors. Now if this is the Argan plane, and this is the point representing a particular complex number z, with its real part and imaginary part acting as the x and y coordinates, then this vector from the origin all the way till this point is called the complex number vector for this complex number z. Now the length of this vector was nothing but the modulus, which is mod z, right? Now we talked about complex number vectors because we wanted to convey this line segment AB and we had no other intention. But the interesting thing is you can actually do a lot more using this representation of complex numbers as vectors. So that's our topic for today. What are the applications of representing complex numbers as vectors in the Argan plane? Now before we go into the Argan plane, let's talk about vectors for a while. What exactly is a vector? From physics perspective, vectors are arrows pointing in space. And what defines a vector is its length and the direction it's pointing to. So as long as you maintain the length and the direction, you can move it all around and it's still the same vector. So you can think of a vector as a step or a movement in a particular direction for a particular distance. Now the end where the arrow points is called the tip or the head of a vector and the other end is called the tail of a vector. And we generally denote vectors with an arrow on top of a particular quantity, right? If this is a line segment AB, then it's AB with an arrow, something like how we denote array. And if this is representing a physical quantity velocity, then we use a single letter alphabet V with an arrow like V bar. And also recollect how we do algebraic operations on vectors. Let's talk about scalar multiplication. Now say this is a vector V bar which has a particular length and a particular direction, and I want to multiply this with a real number, say 3. So what I do is I keep the direction constant, I just scale the length 3 times, right? So I'm increasing the length 3 times, keeping the direction constant. So I get a new vector which is 3V bar. Now what if I multiply with a negative number, say minus 2? Then what we have to do is, for the negative sign, you reverse the direction of the vector and then you multiply it 2 times in length to get minus 2V bar. So if I'm multiplying with minus 1, then you just have to reverse the direction of the vector and you get minus V bar, right? Now what about addition and subtraction operations? If these are two vectors U bar and V bar, then their sum U bar plus V bar is also a vector and is obtained by moving a few steps in the direction of U bar and then moving a few steps in the direction of V bar from that point. Now this resultant movement or the displacement as you call in physics is called the sum U bar plus V bar. Or in other words, you start with the vector U bar and then you move the other vector V bar in such a way that its tail sits on the head of U bar. And then you join the loose ends, this vector is U bar plus V bar. And then what about subtraction, U bar minus V bar? Well, for subtraction, U bar minus V bar is written as U bar plus minus V bar. And then we know how to find minus V bar, right? You just have to change the direction of V bar to get minus V bar. And then you have to add U bar and minus V bar. And then you'll get U bar minus V bar. Now, keeping this knowledge in mind, let's see how we can use this scalar multiplication, addition and subtraction of vectors to talk about addition and subtraction of complex numbers in the Argan plane. So guys, complex numbers behave very much like vectors when represented in the Argan plane. If this is the Argan plane and this is a point P representing a complex number z, then by drawing a vector from the origin to this point P gives me a complex number vector z or z bar. Now this vector gives me all information about this complex number. Now the tip of the vector gives me the point, so it gives me the x and y coordinates and hence the real and imaginary parts. Now the length of the vector gives me the modulus and the direction of the vector gives me the argument. Now if you move this vector keeping the length and direction constant, then you're no longer at the same point. Well, this is the difference from vectors in physics and vectors in mathematics. Vectors in mathematics always start from the origin. So as you see, by moving this vector, we are no longer representing the same point, but the length is still mod z, right? So remember that vectors in mathematics always start from the origin and go outwards. So keep this one thing in mind, that only vectors starting from the origin can be a correct representation of complex numbers in the Argan plane. Now say we have these two complex numbers z1 and z2 in the Argan plane. now with some known real parts and imaginary parts. Now, how do we find the complex number z1 plus z2? Well, from the general form, we know that we have to add the real part separately and add the imaginary part separately. So, z1 plus z2 will have a real part x1 plus x2 and an imaginary part y1 plus y2. So, it should be this point somewhere here, right? And this point gives me z1 plus z2. But you can also find this point by doing a vector addition of complex number vectors for z1 and z2. So let's draw the complex number vectors z1 bar and z2 bar. Now let's add them. Let's take z1 and then let's choose z2 and move it so that we put the tail at the head of z1, and then let's join the other two loose ends, and you'll see that you'll arrive at the same point, which is z1 plus z2. And also, if you notice, this vector z1 plus z2 bar forms a parallelogram with z1 and z2 as its edges and sides, and this z1 plus z2 bar acting as the diagonal. Now what about the complex number z1 minus z2? Now for that, we have to find the vector z1 bar minus z2 bar. So for that, first we need to find minus z2. Now minus z2 is a reflection of z2 about the origin. So this gives me the vector for minus z2. And then let me add that to z1 bar to get this vector z1 bar minus z2 bar. And the tip gives me the point z1 minus z2. Now observe that this also forms a new parallelogram with z1 and minus z2 as the adjacent sides, and the vector for z1 minus z2 acting as the diagonal. And also, if you move this vector z1 minus z2 to the point z2, then this ends up forming the other diagonal of the original parallelogram that we have formed. But note that this vector is not the complex number vector for z1 minus z2, because it's not starting from the origin, but it's only an equivalent version having the same length and the same direction. You guys might be wondering, what is the use of this vector representation when addition and subtraction of complex numbers is already pretty simple using algebra? Well, remember that the length of a complex number vector was its modulus. So if you have two complex numbers z1 and z2, then this length is mod z1 and this length is mod z2. And if you construct a parallelogram with these two line segments as the edges and sides, then the other vertex is nothing but the point z1 plus z2. So the length of the longer diagonal is mod z1 plus z2. And what is the length of the smaller diagonal? Well, we said, remember, that this is an equivalent version of the vector for z1 minus z2. So it should have the same length. And the length of the vector for z1 minus z2 is mod z1 minus z2. So the length of this smaller diagonal here will be mod z1 minus z2. Now this is the most important thing that we are going to learn in this video. Mod z1 minus z2 is nothing but the distance between the points z1 and z2 in this Argan plane, or rather it is the length of the line segment joining the points z1 and z2. So as you can see, we are trying to give a geometrical take to statements related to modulus in the Argan plane. And normally while solving problems, you will come across statements such as mod z minus w, mod z1 plus z2, mod z plus 3, etc. Now we know that moduluses are nothing but distance. So let us try to construe these statements as a distance between 2 points in the Argan plane. Now let's take this example, mod z plus 3. Well, I can write mod z plus 3 as mod z minus of minus 3, because I want it in the form mod z1 minus z2. And what is the point minus 3? It is on the real axis, on the negative real axis in fact. And let's say z is some point which we know. Then the distance between this point z and the point minus 3 on the real axis is nothing but the modulus mod z plus 3. And if you know the coordinates of z, then you can easily find this distance using the distance formula. Now assume that we do not know what z is, and hence we do not know the location of z. And say this particular equation, mod z plus 3 is equal to 3, is trying to define z. Then it means that the distance between the point z and minus 3 is 3 units. So z can be this particular point, which is the origin. It can be this point, it can be this point. And you notice that you'll get multiple points which form a circle with the center as minus 3 and the radius as 3 units. So this is called the locus of z. And it is nothing but the set of all points which form solutions for z. And I think the picture is kind of clear where we are trying to head with this understanding of modulus, vectors and geometry. Complex number algebraic statements can be easily understood by using geometrical visualizations And that is the essence of this video. We will learn more about this in the coming videos, and it will become more clearer by looking at a few examples. Now, before we sign off, let me ask you guys a question. Can we also represent the multiplication and division of complex numbers? That is, the product Z1, Z2 and the quotient Z1 by Z2 also in the Argan plane. Now, think of this as a food for thought. Try it on your own. I won't be answering this. We'll probably discuss this in the next video. But until then, let us summarize. The vector directed from the origin to any complex number Z in the Argan plane is called the complex number vector for that particular complex number Z. Note that complex number vectors always start from the origin. If Z1 and Z2 are two complex numbers denoted by 2 points in the Argan plane, then the point Z1 plus Z2 is given by the sum of the vectors Z1 and Z2. If Z1 and Z2 are two complex numbers in the Argan plane, then the point Z1 minus Z2 is given by the difference of the vectors Z1 and Z2. Mod Z1 minus Z2 is interpreted as the distance between the points Z1 and Z2 in the Argan plane.